Alright, hello, and thanks for tuning back in. So today we're going to continue our discussion of integration, particularly focusing on some more complex functions. So today's video will be dedicated to trigonometric functions and handling the integral of those kinds of functions. So be ready to see a lot of sines and cosines and all of that kind of stuff. So without further ado, let's get into it. And we're actually going to start out with a problem. We're not even going to learn what these integrals are. We're going to try to first find the integral of cotangent of x. So let's see if we can do this. So perhaps we don't know where to start because it's cotangent, and this is the first time we're seeing cotangent. But one way we could start approaching this problem is recalling that cotangent of x is the same thing as cosine of x over sine of x. And this seems a little bit more manageable because we can try to do some u substitution here. And I like to choose my denominators as my u values. Usually that works out. Let's see if it works out here. So I'll let u equal sine of x. And then du, we take the derivative of sine of x, and that we know to be cosine of x, dx. So now when we rewrite the integral, we have the integral of cosine of x divided by u, and dx is equal to du divided by cosine of x. And we see that sure enough, we do get this nice little cancellation. So that leaves us with the integral of 1 over u times du, and we learned from our last video that this is equal to the natural log of the absolute value of u plus c. Now we just have to substitute in what u is, and that's going to be equal to the natural log of sine of x plus c. And just like that, we found the integral of cotangent of x. So that's pretty exciting. Unfortunately, not all of them are going to be that simple. For example, this is cosecant. We're actually going to change this a little bit. Let's do the integral of secant of x. So we can start by writing this as like 1 over sine of x dx, but it's kind of hard to progress from there. We could try u substitution with sine x, but then we won't have anything to cancel with, and it's like, I don't know. It's hard to progress from here. So, we're going to utilize a trick, which whoever thought of this is an absolute genius. But what we're going to do is we're going to take secant of x and multiply it by 1, right? Except we're going to multiply it by a form of 1, and we're going to multiply it by a fraction which equals 1, right? So we see this in algebra where we multiply something by like 2 over 2 or like 4 over 4. And the reason why I say this person's a genius is because we're going to multiply it by secant of x plus tangent of x over secant of x plus tangent of x. And I don't expect you to be able to come up with this on the spot. I don't expect many people to be able to come up with this on the spot. This is purely just a demonstration of how one would calculate this integral. In the next slide or so, I'll show you all of the trig functions and their integrals, and you can just memorize those, because computing this is not easy to think of. But this is just for demonstration purposes. So now let's see what happens when we multiply that secant x to the numerator. We get, secant squared x plus secant x tangent x. All of this over secant x plus tangent of x dx. And you're like, well, this doesn't look much better. And it's not, because we're going to have to use u substitution here. And our u is going to be secant of x plus tangent of x. Goodness. And now we have to find du. So hopefully we still remember the derivatives of these trig functions. So the derivative of secant x is secant x tangent x, and the derivative of tangent x is secant squared x. And now we can see that our integral becomes secant squared x plus secant x tangent x, all of this over u times du over secant x tangent x plus secant squared x. And sure enough, our numerator and denominator cancel. It's just like magic. We're left with the integral of 1 over u du. That's equal to ln of the absolute value of u plus c, which is equal to ln of secant x plus tangent of x plus c. Absolutely crazy how to solve this integral. Much more difficult than the previous example, where the previous one was just a use substitution. Here we had to do this crazy multiplication, but like I said, you shouldn't be expected to come up with that necessarily. But I think the main thing here is that sometimes, if the integral seems hard, see if you can multiply by some form of 1. Maybe that'll help you. It's just an idea. But this was, again, just a demonstration. And now, what you've been long awaiting. The integrals of our trig functions. So, like I said, some of these integrals can be quite challenging. And so, this list you should be familiar with. I encourage memorizing them, but I guess it's not necessary. So, we can see some similarities. So, sine goes to negative cosine, and cosine goes to sine. So these two are like kind of related to each other. Tangent goes to negative ln of cosine of u. Cotangent goes to positive ln of sine of u. We see here secant is this, which we just computed. Cosecant is similar, but slightly different. And then these are some other forms that we might get. And the reasons why we get these forms is because, for example, secant of u, the derivative of that is secant u tangent u. Similarly, derivative of negative cosecant of u is this. So these are some things we may see in the integrand, and it may be helpful to be familiar with these. So again, it's good to be familiar with these. It's even better to memorize them, but these are here for your convenience. Let's do another example. So the integral of 2 minus tangent x over 4. Okay, so the tangent's a little bit frightening, but we can handle the 2. So we can rewrite this as the integral of 2 dx minus the integral of tangent of x over 4 dx. And then this is going to be 2x minus the integral of tangent of x over 4 dx. So how are we going to handle this integral of tangent of x over 4? Well, if we scroll back a little bit, we know how to handle this tangent of u thingy here. So let's try to get it in the form of tangent of u. So to do that, let's let u equal x over 4, and that would mean that du equals 1/4 dx. And now we can rewrite 2x minus integral of tangent of u, and then dx is going to be equal to 4 times du. Okay, so now we can bring out that 4, we get 2x minus 4 integral of tangent of u du, and now we know how to handle this tangent of u. If we scroll back a little bit, we see that's equal to negative ln of the cosine of u. So this would be equal to 2x minus 4 times negative ln cosine of u. I'll tack on the plus c because it's an indefinite integral. We see that the minus signs will form a plus sign together. So this is 2x plus 4 ln cosine, and let's substitute u in. U was x over 4 plus c. And that would be this integral. So not too bad, just a little bit of u substitution there, and then using the integral of tangent. So yeah, that's just a typical integral that we may come across. What about this? This seems a little bit challenging. But again, we can handle if we have secant of u and tangent of u. So if we let u equal 2x, then we're kind of in business. So let's do that. U equals 2x, du equals 2 dx. And then our integral becomes integral of the secant of u plus the tangent of u, and then dx is equal to du over 2. Okay, so what we can do here is we can bring out like the 1/2, and we're multiplying that with the integral of secant of u plus tangent of u du. But let's break apart the integral into 2. And now we can handle secant of u and tangent of u. So secant of u, if we remember, let's see what it is, I kind of forgot. Ln of the absolute value of secant u plus tangent u. So this would be ln of the absolute value of secant u plus tangent u. And then for tangent u, we just used that in the previous one, that's negative ln of cosine of u. So this would be minus ln, absolute value, cosine of u. And now we just have to substitute our u back in. So this would be 1/2 times ln of secant of 2x plus tangent of 2x minus ln cosine of 2x. And tack on that plus c. Don't forget the plus c. And that's our answer. So a little bit more complex here, but again, using that u substitution and then going back to our fundamental equations. And that gets us in good shape. So yeah, that's our introduction to the trig functions. There is, however, quite a bit more to explore with these trig functions. But before we do that, we have to talk about what inverse functions are. You may be familiar with inverse trig functions, and that would be a great foreshadowing of what we'll be doing later on in this video. Before we get to that, we should have a strong understanding of inverse functions. So let's take a look at what inverse functions are. So we'll call g of x the inverse of f of x if, when we plug in g of x to our function f, we get x. So f of g of x equals x, and g of f of x equals x. And that implies that if g is the inverse of f, then f is the inverse of g. So typically, our notation of the inverse of f of x is given by f to this -1 of x, and we read that as f inverse of x, so not f to the -1. And then here we see some examples of inverse functions. So 2x goes to, or the inverse of 2x is 1/2 of x. So we can check this. We need to have f of f inverse of x equal to x. So f of x is 2 times x. So where we see an x, we should plug in f inverse of x. So this would equal 2 times, I guess we'll just write it out, f inverse of x, which is equal to 2 times 1/2 x, which is equal to x. So that does indeed check out. And we can do the same thing here with this. Square root of x squared is x. Similarly, e to the ln of x is also equal to x. And we can obtain inverse functions by switching the x and y variables, where this is sort of our y, and then solving for y. We also should be familiar with something called the horizontal line test. And this says that if there exists a horizontal line such that it crosses a function more than once, then the function fails the horizontal line test, and that function does not have an inverse function. So we got this cubic looking function down here in red, and we have this black horizontal line, and we see that it intersects the function 1, 2, 3 times, which is more than once. So this function does not have an inverse because it fails the horizontal line test. Whereas if we take something like, we just saw e to the x had an inverse, so that's the graph of e to the x. no matter what horizontal line we draw, it can never cross through it more than once, so this passes the horizontal line test, and it does have an inverse. I'll just notate this here, e to the x. So this is a good test to know if a function has an inverse. Now there's some properties about inverse functions that we should be relatively familiar with. And the first one is about continuity. So if f is continuous, then f inverse is also continuous. Then we have stuff about increasing and decreasing, where f and f inverse are similarly related in whether they're increasing or decreasing. Differentiability also carries through, so if f is differentiable on an interval containing c, and f prime of c does not equal 0, then the inverse is also differentiable at f of c. Interestingly, if f contains the point a comma b, then f inverse contains the point b comma a, and that's kind of a result of how we solve for the inverse, where we swap the variables. And what I think is the coolest part is that the graphs of f and its inverse are reflections over the line y equals x. So we see a nice little picture here, where in red we have the graph of e to the x, in black we have the graph of ln of x, which is the inverse of e to the x, and then in blue we have the line y equals x, and we can see that e to the x and ln of x are mirroring each other about the line y equals x. So I think that's pretty neat. Cool. So our first task is to find and verify the inverse of f of x equals 2x cubed minus 1. So to do that, we have to swap the x and y variables. That's what I said we do. So we can rewrite this as like y equals 2x cubed minus 1. So that's a good step. And so now we need to do the swap of the variables. So now we're going to write this as x, let me do it underneath it, x equals 2 times y cubed minus 1. And now our goal is to solve for y. So we have x equals 2y cubed minus 1. That tells us that 2y cubed is equal to x plus 1. That tells us y cubed equals x plus 1 over 2. And finally, y is equal to the cube root of x plus 1 over 2. So this indicates that f inverse of x equals the cube root of x plus 1 over 2. So that would be finding our inverse function. So now we have to check to make sure that we are indeed correct. So we have to verify that f of f inverse of x equals x. So that means we have this equation up here, f of x, but now wherever we see an x, we have to replace it with f inverse of x. So this would be equal to, so f of f inverse of x is equal to 2 times f inverse of x cubed minus 1. And then we have f inverse of x over here. So this would be 2 times the cube root of x plus 1 over 2 cubed minus 1. The cube root and the cube cancel. We're left with 2 times x plus 1 over 2 minus 1. The 2's cancel here. We're left with x plus 1 minus 1, which is equal to x, which is what we wanted. So our inverse function is here cube root of x plus 1 over 2. Cool. Now let's talk a little bit about the derivatives of inverse functions. So we have a definition that if g is the inverse of f, then g prime of x is equal to 1 over f prime of g of x. And the proof for this is actually using the chain rule. By the definition of inverse function, if g is the inverse of f, then this is the property we have. This is the property we just showed in the previous example, or it's the property we used to verify that we had an inverse function. So this we know must be true. So if we take the derivative on both sides, this should look eerily similar to the chain rule, because it is the chain rule. And sure enough, when we take the derivative, we get this, which is the definition of the chain rule. The derivative of x is just 1. So now we just solve for g prime of x, and we get this. So it's like a special case of the chain rule, where the chain rule on the left-hand side equals 1, right? Only because we have this property up here. So pretty neat proof, but also a pretty handy formula. So let's try to use that in practice here. So f of x is given by this cubic formula here. We're asked to find what is the value of f inverse prime of 3. Pretty weird notation. Well, in the previous slide, we said that if g is the inverse of f, then we have a formula for g prime of x. Well, if we let g equal the inverse of x, then we're solving for g prime of 3, which we have a formula for. So we'll do just a tiny bit change of variables here, just so it's a little bit more pleasant to look at. So that means g prime of 3 equals 1 divided by f prime of g of 3. Okay, so for that to happen, we still need to solve for g of 3. We also have to find f prime of x. So it's still quite a bit more to do, but it's not too bad. So let me just erase this here, or let me move this here. Okay, so we have, let's say, y equals 1/4 x cubed plus x minus 1, right? That's kind of the formula we're working with here. And we're going to, we need to do this swapping of variables. So we get x equals 1/4 y cubed plus y minus 1. Okay. So solving for y looks a little bit tricky here, but we can still work with this. And the reason why is we need to solve for g of 3, right? That's kind of the reason why we're solving for the inverse, to compute g of 3. So that means, so let's just imagine what happens. So we're going to get y equals something in terms of x, right? And we'll call it f inverse of x, which is equal to g of x. And then we want to find g of 3, which means wherever we see an x in our equation, we're going to plug in a 3. And that will give us the value of y, which is what we're trying to find right here. So what we can do is we don't even need to worry about finding the inverse in general. We can find the inverse at a specific point. So why don't we just plug in x equals 3 now, and then solve for y, and that will give us g of 3. So with that in mind, we're going to put in a 3 in for x. This equals 1/4 y cubed plus y minus 1. Okay, so now let's try solving for y. This tells us that 1/4 y cubed plus y equals 4. Can factor out a y. Y times 1/4 y squared plus 1 equals 4. Actually, before we do that, let's multiply through by 4. So we get y cubed plus 4y equals 16. And further, now we can factor out the y. Y times y squared plus 4 equals 16. And then, well, there's a couple ways of solving this, but we can start thinking about what will happen. So y squared is always going to be positive, so this quantity here will be positive. And what we see is when y equals 2, we get that expression equaling 16. So all of that to say that g of 3 equals 2. But now we want f prime of g of 3, which is equal to f prime of 2. So first let's find f prime of x. So f of x we were given is 1/4 x cubed plus x minus 1. So that tells us that f prime of x, this will require power rule, so this is 3/4 x squared plus 1. Now we can solve for f prime of 2. F prime of 2 equals 3/4 times 2 squared plus 1, which is equal to 3 plus 1 equal 4. Therefore, g prime of 3 equals 1 over f prime of g of 3, which we said was equal to 1 over f prime of 2, which is equal to 1 over 4, and that's our answer. So, what are the key takeaways here? First thing, notation can be yucky at times. So if it helps, you can just change f inverse to something like a g. Just make sure you have a clear understanding of which function is which, and know that, okay, f inverse is not different from g, they're the same thing. Second, you don't always have to solve for the inverse directly. If you're solving for the inverse at a particular value, just plug that in, and then solve for that g of 3 in this case. And lastly, know your formulas. That's about it. So that's our introduction to inverse functions. So now, let's talk about inverse trig functions, which maybe you've heard about. However, maybe you're thinking something's wrong, right? Something seems wrong. Perhaps you've noticed this, that we said that a function has an inverse if it passes the horizontal line test. But we see here we have the graph of sine of x. This is the graph of cosine of x. This is a version of one of the tangent graphs. It's, I think, tangent of x over 3, it says. These don't pass the horizontal line test. So how can we have inverse trig functions? You must be lying to me. And indeed I am. There is no such thing as inverse trig functions. End of it. I'm joking. There are inverse trig functions. And the way we get these functions is we take advantage of the periodicity of these trig functions. Right, so like sine of x has period 2 pi, where it just repeats this, which is length 2 pi. Same thing for cosine of x. So we'll restrict our functions just to look at one period. And in that case, just looking at this period of cosine of x, I guess that's not the best example here. But we can restrict our sine of x function, perhaps this much. And we can say that, okay, if we look here, within this bounds, this does not fail the horizontal line test, right? So we have this little bit which repeats itself over here, but it's also flipped here. Hopefully that made sense. But this is a little bit more specific. So to ensure that trig functions don't fail the horizontal line test, we'll take advantage of the periodicity, and we'll restrict the domain of the trig functions to allow them to have an inverse. And here we can see the graph of what we call arcsine and arccosine, which are the inverse trig functions of sine and cosine respectively. So now we have to think that, okay, with sine, normally sine of x, we plug in some value which is in degrees or radians, and we get something in the range of like -1 to 1. Now with arcsine of x, we plug in something, so -1 less than or equal to x less than or equal to 1. So now our domain is restricted to this bound, and our output, in this case, will be between -pi over 2 and pi over 2. So that's what arcsine looks like, and arccosine is pretty similar, just shifted upwards a bit and reflected, but that's just because the two functions are different. So let's take a look at the notation, and we'll use this notation interchangeably. So where we see this -1 thing representing inverse, we'll still use that with the trig function, so this reads inverse sine of x, but we can also say arcsine of x. So this arc notation, I think it's been losing popularity recently, which is a shame because I really like it. So it's familiar, it's handy to be familiar with because you'll see it not necessarily on exams, but maybe in other math literature, so it's good to be familiar with it. But we'll use these interchangeably. I think some of these next examples will use arc a lot because I really like arc. Okay, so let's take a look at the derivatives of these inverse trig functions. And they're all here. They're a little scary, but we can see some parallels. So if we look at arc sine and arc cosine, these two look very similar to each other. The only difference is this is -1 and this is +1. Similarly for inverse cosecant and inverse secant, very similar to each other, just the -1 and +1 are different. And inverse tangent and inverse cotangent, very similar, -1, +1. So they're super similar, and they do look scary. I mean, admittedly, this does look like not a fun thing to memorize. But memorizing will help you a lot, because seeing these types of functions, at least the shapes, what they look like, where we have a u squared minus 1 squared in the denominator, that will help us out a lot. You can imagine eventually we'll talk about integrals, and if we draw an integral symbol here, we would want to be able to recognize this pattern, so we know that, okay, this is going to be arc cosecant, something like that. So I highly encourage memorizing them. But in case you don't, let's try to derive the formula for the derivative of arc sine of u, and hopefully this, after seeing this, you'll be convinced that you should memorize the formula. So this will be a little bit of a demonstration, but I encourage you to follow along because it is still very educational. So what we're going to do here is it's going to require a little bit of creativity. The first thing we're going to do is we're going to let y equal this arc sine of u. And then what we'll do is we'll take the sine of both sides. So we'll take sine of y equal to sine of arc sine of u. Well, on the right here, sine and arc sine are inverses, so this will just evaluate to u. So we have sine of y equals u. So this should feel like a little similar to what we did with like taking natural logs of both sides before taking the derivative to make things look a little bit simpler, perhaps. But this requires, quite a bit more creativity. So if sine of y equals u, let's draw a right triangle. So this is our right angle. We have an angle here called y, and if the sine of y is u, then the opposite side we can label u, and the hypotenuse is 1. So by definition, there we have opposite over hypotenuse is equal to u. We also have a third side, which we'll call b, and using the Pythagorean theorem, we can say b equals the square root of 1 minus u squared. Okay, so we're making a little bit of progress. Let's see what happens when we take the derivative of both sides of this. So d dx of sine of y equals d dx of u. So on the right-hand side, we're just left with du. And on the left-hand side, we'll have to do some implicit differentiation. So that would be cosine of y times dy dx by implicit differentiation. And we're trying to solve for dy dx. So dy dx equals 1 over cosine of y times du. Well, what's cosine of y? Let's take a look at this triangle here. Cosine of y is equal to adjacent, which is b, over the hypotenuse, which is 1, which is equal to b equal to the square root of 1 minus u squared. So if we plug that in, now we get 1 over square root 1 minus u squared times du. And that is exactly what we got up here. So hopefully this convinces you to memorize the formula, because to solve this, there's so much creativity involved in taking the sine of both sides and then utilizing a right triangle drawing. So please memorize the formulas. Let's do an example. So this hopefully doesn't look too scary. We see an arc cosine, which is okay, but we know how to handle arc cosine of u, right? We just showed that d dx of arc cosine of u is going to be equal to negative 1 over square root 1 minus u squared times du. So let's let u equal the square root of x. Then d dx of arc cosine of the square root of x is going to be equal to d dx of arc, whoa, my handwriting is not good today, arc cosine of u, and that we know is to negative 1 divided by square root 1 minus u squared times du. So now we just have to find what du is, and for that we'll have to use the power rule. So if u equals square root of x, that's equal to x to the 1/2 power. Taking the derivative, du equals 1/2 x to the negative 1/2 power dx. Okay, so now we can do a little bit of substitution here, and we get negative 1 divided by square root 1 minus u is equal to the square root of x. We're squaring that, and then we're multiplying that by du, which is 1/2 x to the negative 1/2 power. Okay, so in the denominator, what do we have? We have negative, well, numerator is negative 1. Denominator is 1 minus x, because square root of x squared is just x. And then we're multiplying that by 1 over 2 square root of x. Right, that's just rewriting this as a square root. And we're basically there, but we can, make this look a little bit prettier by saying this is negative 1 over 2 square root x minus x squared, something like that. And that would be our answer. So just a simple example, but remember, when you know how to do arc cosine of u or something of u, try to get it in that form using a u substitution of sorts. And that would be that. Cool, let's move onward. Now this one looks a little bit more challenging. Find the points of inflection of y equals arctangent of x squared. Do we remember what the points of inflection are? So points of inflection are where the second derivative equals 0. So we have to compute the second derivative of this function. So we have y equals arctangent of x squared, so y prime, that seems like it's going to use the power rule, chain rule type thing. So we do 2 times arctangent of x to the power of 1 times d dx of arctangent of x. Okay, so then what's the derivative of arctangent of x? Hopefully we remember that from a couple slides ago. This is arctangent of x divided by 1 divided by x squared plus 1. That's our formula. And we can rewrite this as 2 arctangent of x divided by x squared plus 1. Nice, not too bad. But now let's find the second derivative. And that'll be a little bit worse. Y prime prime. What are we thinking? How are we going to solve this? Looks like a quotient rule type thing to me, so let's do that. So we would be doing x squared plus 1 times the derivative of the top, 2 arctangent of x, minus 2 arctangent of x, times the derivative of the bottom, which is x squared plus 1, all of this divided by the square of the bottom. Let me just make sure I got that right. Don't want to be leading us down the wrong track. Yes, that seems right. So this would be x squared plus 1. Derivative of 2 arctangent of x is going to be equal to 2 times derivative of arctangent of x, which we just said is 1 over x squared plus 1, minus 2 arctangent of x. Derivative of x squared plus 1, that's just a good old 2x. And we're dividing this all by x squared plus 1 quantity squared. And we can see that some things will cancel. This x squared plus 1 cancels nicely. So that leaves us with 2 minus 4x arctangent. X divided by x squared plus 1 squared. So that's our second derivative. And we want this to equal 0. So for this to equal 0, we need the numerator to equal 0. Right? So we want 2 minus 4x arctangent of x to equal 0. Which means we want 2 to equal 4x arctangent of x. And we want 1/2 to equal x arctangent of x. And this is not easy to solve by hand, so you can use a calculator. Should get x equals plus or minus 0.765. And those are our points of inflection. So, yeah, good little practice of remembering what points of inflection are, and some quotient rule practice, which feels like we haven't done in a while. But, yeah, good question here. Let's do another one. Find the slope of the tangent line of this, which I guess I'll highlight just to make it stand out a little bit better, at the point negative pi over 4 comma 1. So what's our game plan? We need the slope of the tangent line. So we need to compute dy dx, and then find dy dx when x equals negative pi over 4. That's our two-step game plan. So how are we going to find dy dx? Well, we'll take the derivative, but to do that, we'll have to use some implicit differentiation. So d dx of the left-hand side, x arctan of y, equals d dx of the right-hand side, y minus 1. Okay, left-hand side, d dx of x squared is 2x, plus, well, for this x arctan of y, that seems like we're going to have to use the product rule. So let's do that. First, times the derivative of the second, plus the second times the derivative of the first. And on the right-hand side, d dx of y minus 1 is just dy dx. Okay, let's handle that left-hand side a little bit better. 2x plus x times derivative of arctangent of y. So again, we treat y normally, we take the derivative of it normally, and then we take the derivative of the inner function, so like a chain rule type thing. So this would be 1 over y squared plus 1 times dy dx plus arctan of y times 1. This we said equals dy dx. We want to solve for dy dx, so let's sort of take this term here to the right-hand side and then factor out our dy dx. So this would tell us that 2x plus arctan of y equals dy dx minus x over y squared plus 1 times dy dx, dy dx. We'll factor out a dy dx now. So we left with 1 minus x over y squared plus 1. And that equals 2x plus arctan of y. And now we can solve for dy dx just by taking the quotient of the two. So dy dx equals 2x plus arctan of y, all of this divided by 1 minus x over y squared plus 1. So we've solved for dy dx, which is incredible. Now, we just need to find the slope of the tangent line at this point. So where we see an x we'll plug in negative pi over 4. Where we see a y, we'll plug in a 1. So at negative pi over 4, comma 1, dy dx equals 2 times negative pi over 4 plus arctan of 1, all of this divided by 1 minus negative pi over 4 divided by 1 squared plus 1. So this is going to equal negative pi over 2. We have to think, what's arctan of 1? Well, that would be so whatever arctangent of 1 is, let's call that x, then that means tangent of x should equal 1. So that occurs at pi over 4. We divide that by 1 plus pi over 4 divided by 2. So if we simplify this a little bit, we get negative pi over 4 divided by 1 plus pi over 8, which is equal to, simplify this a little bit more, negative 2 pi divided by 8 plus pi, just multiplying the numerator and denominator by 8. And that's our answer. So a little bit of a harder problem here, but still good nonetheless. Cool. Let's just talk a little bit about the relationships. I pointed this out when we were looking at the derivatives. And it's that these sine and cosine, arcsine, arccosine, are related by this negative 1 factor. Remember, the numerators differed 1 versus negative 1. And we see that for arcsecant, arccosecant, same here for inverse tangent, inverse cotangent. And because of that, we only really need to define or memorize 3 integrals or 3 derivatives. And the reason for that is an integral equaling arc cosine of x is the same thing as a negative arc sine of x. So we don't really need to worry about arc cosine of x. So let's take a look at our integrals here. So this is where it goes back to saying that remembering those forms of the derivatives is really helpful, because we see those kind of forms here. So the integral of 1 over a squared minus u squared du is arcsine of u over a. And we have definitions for arctangent and arcsecant. And the main thing here is a is some constant in this case. Does it have to be greater than 0? I don't know if it has to be greater than 0. I think just a squared has to be greater. Actually, no. Never mind that. Do know that it should be greater than 0. Anyways, so, yeah, these are the 3 to be familiar with, but the most important thing is knowing what these look like, where we have a square root of the difference of squares, or in the denominator, it's the sum of squares, or u times the square root of the difference of squares, and associate those with arcsine, arctangent, arcsecant, things like that. Let's try to do a problem here. So we have x times 4 square root of 4x squared minus 9 in the denominator. So you might be tempted to do some sort of u substitution with the 4x squared minus 9, but you'll shortly realize that we can't actually cancel this x. If this x was in the numerator, then we could do u substitution and we'd be good. But since it's in the denominator, it's a little bit tougher. So let's take a look back up here. Which of these 3 is what we're looking at most reminiscent to? In my opinion, it's this third one down here, where we have u being a function of x on the outside, which is this. We have u squared, so the function of x squared minus some constant. So function of x minus some constant. So our target should be something in this form. That would sort of be what we're looking for. So let's try to do that. Let's let u equal 2x. Why 2x? Because u squared equals 4x squared, which is what we were making the connection with here. Okay, we'll need du, that equals 2 times dx. And we also have that x equals u over 2. These are just some things we've gathered. So let's try to do this u substitution and see what happens. So we have the integral of 1 over x square root of u squared minus 9. But this x we can write as u over 2, so why don't we do that? This is u over 2, so that's looking good. And then dx is equal to du over 2. So we can see that this 2 and this 2 down here will cancel with each other. So we're left with the integral of 1 over u square root of u squared minus 9 du. And now we're pretty close, right? We have u on the outside, we have a square root, we have the u squared, now it's just this a squared thing here. Well, if we let a equal 3, then we have the integral of 1 over u divided by the square root of u squared minus a squared du. Right, just substituting that with a variable. And there we go. We get our thing right here, so let's do the substitution. So this would be equal to 1 over a times arcsecant of u over a plus c. So now we just have to make the substitutions for a and u. A is equal to 3, so this would be arcsecant. U, we said in the beginning, was 2x. A is still 3, plus c, that's our answer. So with questions like these, the first step is always to see what does this integral seem reminiscent of. And once we have a target, in this case, we determined that our target was to get it in this form. You can do substitutions with variables like this and get it into this form, right? All we did was set u equal to something, set a equal to something, and we wrote our integral in this form. And then we could use the formula here. But once we do that, we need to make sure to substitute these variables back in, and also be careful of like this du instead of dx. So a little bit care is needed, but that's the general pattern. What about this? What about this? So what is this most reminiscent of? Let's scroll back a little bit. It's not this one because we have a square root in the denominator, so it's probably similar to one of these two. And it's kind of hard to tell the difference. I'll just rewrite what we're trying to solve for. E to the 2x minus 1. Right, you can make arguments for the case of both the top and the bottom one, right? In the top one, we're taking the difference of two squares, except here we are doing that. It's just that the function of x comes first and here it comes second. But for this third one, we have that where the function of x comes first and the constant term comes second, but we have this function of x on the outside. So it's hard to choose. So let's try to, one thing we concluded is that our function of x should be related to this e to the 2x. So we want u squared to equal e to the 2x, so we'll let u equal e to the x. Let's see what we can get out of this. Du equals e to the x dx. Okay, so now let's try to rewrite the integral. This is the integral of 1 over square root of u squared minus 1, and dx is equal to du over e to the x. So let me just rewrite it like this. Bring the e to the x in the denominator. Now hold on a second. E to the x. We said u is equal to e to the x. So what if we just put a u here instead of e to the x? We're totally allowed to do that. 1 over u square root of u squared minus 1 du. And would you look at that? That looks a lot like this. So if you were debating between these two and you chose the third one, good for you. Congratulations. But if you didn't choose that correctly, don't worry about it. It's kind of hard to see that. So we'll let a equal 1, And then we have the integral of 1 over u, square root of u squared minus a squared, du, which is equal to 1 over a, arcsecant of u over a plus c, and a is equal to 1, u is equal to e to the x, and now we're just left with the arcsecant of e to the x plus c. So a little bit crazy stuff here with our u substitution, but again, seeing what this is familiar to. Like, we could try doing u substitution without anything else, but we would see that we can't cancel anything. So having an idea that, oh, square root on bottom with the difference of squares, that's kind of similar to inverse trig functions, that's a good first step. Couple more problems, and then we'll call it a night. So evaluate this following integral. This seems tough. Again, you could try to approach it with u substitution, but what's there to cancel with? The numerator is just 1. And, well, now you're thinking that, okay, we're probably going to use inverse trig functions because that's all we've been talking about this video. So we'll scroll back and taking a look at these three. Which one is the most similar to? Hopefully you're all choosing the correct integral on this one, and that would be the second one. And the main reason for that is we don't have a square root in the denominator. And why introduce one if we don't need one? So here we're taking the sum of the squares of two things, where one is a constant and the other is a function of x. So ideally, we would like to write this as the sum of two squares. It's hard to do that directly. And can we factor this easily? No, not really. It would require the quadratic formula, which just doesn't seem like the right thing to do. So why don't we try completing the square? So if we have x squared minus 4x plus 7, that's the same thing as x squared minus 4x plus 4 divided by 2 squared. Actually, the minus 4 over 2 plus 7. Let me go back to red to keep this the same. And then we'll subtract off that minus 4 over 2 squared. So this is going back to completing the square. So this is equal to x squared minus 4x plus 4, then plus 7, and then we subtract off the 4. So we're adding 0 to our equation. But we see now that this can be factored into x minus 2 squared. 7 minus 4 is 3. So our integral can be rewritten as 1 over x minus 2 squared plus 3, which is pretty close to what we wanted, right? We wanted a function of x squared, and we have that now. We just need the constant squared. So let's let x, well, we want, let me use pink. We want a squared to equal 3. So let's let a equal the square root of 3. And then we have integral 1 over x minus 2 squared plus a squared dx. We can let u equal x minus 2, and du equals dx. And then we're left with the integral of 1 over u squared plus a squared times du. And now we can scroll back and laugh because, aha, we have found this integral. We've extracted it from our problem. So we'll use this equation here. 1 over a times arctangent u over a plus c. 1 over a times arctangent u over a plus c. And then do our substitution. So this would be 1 over the square root of 3 times arctangent of x minus 2 over the square root of 3. Don't forget your plus c. So just like that. A little bit sneaky here. So when we see this kind of polynomial in the denominator, maybe think about completing the square. But later in the semester, later in future videos, we'll learn another way of handling integrals with polynomials in the denominator. So be on the lookout for that. But for now, consider completing the square. Just another trick to add to your toolbox. Okay, multiple choice question. Finally, we can take a sigh of relief because we can guess on this question. No, we're not going to guess. We're gonna actually solve this. How many zeros does f prime of x have on the closed interval 0 to 2 pi? So we need to take the derivative of f of x. So f prime of x, let's see, e to the sine of x. So let's see, how do we do the derivative of e to something? We keep that e to something and take the derivative of the something. So this would be equal to e to the sine of x times the derivative of sine of x. So that's equal to e to the sine x times cosine of x. And we want this to equal 0. Well, now we have to be a little careful. What does e to the sine x look like? Well, sine of x oscillates between -1 and 1, right? So sine of x is in between 1 and -1. And if we think of the graph of e to the x, that looks something like this. So if we restrict our field of vision to -1 to 1, we're only looking within this area here. And that section of the curve is always positive. It's never equal to 0. So that means e to the sine of x is greater than 0. So that means the only time this function up here will equal 0 is when cosine of x equals 0. So cosine of x equals 0 when, well, we have to think about our unit square or unit circle, and that's when x equals pi over 2 or 3 pi over 2. And so there are 2 points where f prime of x equals 0, so our answer is b equals 2. And remember, we're looking on the interval here, so that's why these are our only 2 zeros. So you're like, what does this have to do with trig functions? Nothing. It's just good practice from previous things that we've learned. And now we move on to our last question. So we're given a table, and we're given that f and g are differentiable for all real numbers, and g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function of h is given by this here. Explain why there must be a value r for 1 less than r less than 3 such that h of r equals -5. Okay. So this is a little bit of an interesting problem here. And maybe it's a little bit hard to figure out what we need to do to find this h of r equals -5, since we're only given a few values in the table. But notice how our domain for r is restricted between 1 and 3. So why don't we just take a look at h of 1 and h of 3 and see what happens. So h of 1 is equal to f of g of 1 minus 6. G of 1, let's use green. G of 1 is this value here, which is 2. So this is f of 2 minus 6. And f of 2 is 9. So 9 minus 6, which is equal to 3. H of 3 is going to be equal to f of g of 3 minus 6. So now we need g of 3. That would be 4 here, minus 6, and now f of 4 is equal to -1, which is equal to -7. Okay, so let's try to draw a picture here. Sometimes that helps visualize what's going on. So h of 1 is somewhere here, and then h of 3 is somewhere down here. I guess that's not to scale, but whatever. And this is 3, this is negative 7. And we have some function h which connects these two somehow. And we want to say that there's some point between this interval where h of r equals negative 5. So we'll draw this line here at negative 5. And sure enough, we find this point here. So how do we formalize that? Hopefully you remember that there's a theorem that helps us about this. It helps us with this. And that's the intermediate value theorem. So we can write that since h of 1 is greater than, or sorry, h of, let's write it differently. Negative 5 is less than h of 1, and negative 5 is greater than h of 3, by the intermediate value theorem. So we have to cite that theorem. There must be some r within the interval negative 1 less than r less than 3, such that, 1 is less than r less than 3, such that h of r equals negative 5. So this is just recalling what the intermediate value states. Intermediate value theorem states. So this negative 5 could have been like 0 or 1, 1.5, negative 6. It just has to lie within these two endpoints. So if this is confusing, I highly encourage you to review what the intermediate value theorem states. And always remember, you can just cite it like this and then make your conclusion as follows. Let's take a look at B. Now we want to say that there's some point within that same interval such that the first derivative of h at that point equals negative 5. So this requires a little bit of creativity, perhaps. What we can do is we can use the mean value theorem. The mean value theorem. So again, I encourage you to review what this theorem states if it's confusing. And what that basically says is we can take our two endpoints, sort of draw the line that connects the two, find the slope of that line, and that means that there is some point within that range, in between those 2 points, such that the slope of the tangent line equals the slope connecting these 2 points. You're like, well, why are we going to do that? Because we'll see that h of 3 minus h of 1 divided by 3 minus 1 is negative 7 minus 3 over 3 minus 1. That's equal to negative 5, which is what we were looking for here. So by the mean value theorem, there exists some c such that 1 less than c less than 3, where h prime of c equals negative 5, and that's by the mean value theorem. So again, recalling those two formulas those two theorems is very important. Let's take a look at C now. We're given w of x equals this, and we want to find w prime of 3. So w of x equals the integral of 1 to g to x of f of t dt. And we want w prime of 3. So there's a couple ways of solving this. Sometimes you can just take the derivative right away and try to do cancellation with the integral. I personally tend to avoid doing that just because I don't like handling these limits when I'm trying to cancel a derivative and an integral. I just don't feel comfortable doing that. So what I'll do is I'll solve this integral first. You're like, how am I going to solve that? I don't know, there's nothing to solve there. And you're right. So we'll just notationally solve it. We'll say that the integral of f of t is equal to capital F of t. That's sort of the notation we use. And that's going to be evaluated from g of x down to 1. So fundamental theorem of calculus, we get f of g of x minus f of 1. Now recall that when we evaluate this, it's going to be a function in terms of t, right? F of t is a function in terms of t, but when we plug in t equals 1, f of t will equal a constant. And the reason I mentioned that is because this still equals w of x. W prime of x is equal to d dx of that entire quantity. And if f of 1 is a constant, then the derivative of a constant is equal to 0. So this would just be equal to d dx of f of g of x. And for that, we'll have to use the chain rule. So the chain rule will have to take the derivative of the outside function. So the derivative of the capital F would be lowercase f, and then we keep the g of x, and multiply it by the derivative of the inner function, g prime of x. And now we can solve for w prime of 3. So w prime of 3 equals f of g of 3 times g prime of 3. So we have to go back up to the table. So g of 3 is 4, g prime of 3 is 2, so we'll keep those in mind. So this would be f of 4 times 2, and f of 4 we said was negative 1. So this is equal to negative 1 times 2 equals negative 2. And that's our answer. So these last couple of questions we did were just review of some of the concepts we've talked about previously, but it's still just very helpful to always practice these things and be aware of them. Hopefully you found this video helpful. We covered a lot about trig functions and their inverses, and if there's one thing I suggest to you, one thing I encourage you to do, is to memorize those integrals and derivatives of the inverse trig functions. Because like we showed in some of these examples, where is it? Nope, not these. Some of these, this one here, and then this one here, and then this one here. We had to cosmetically tell what these integrals were similar to, and then alter them in a way that we would get to our desired structure. So being familiar with those shapes is really important, and that's why I suggest memorizing them. Anyways, thanks for watching, hope you learned a lot, and until next time, take care.